Greetings, welcome to this new video about Norton's theorem. In this video, I will show you how to use Norton's theorem with an easy to follow example. By watching carefully, you will learn how to apply Norton's theorem to solve practical problems. Let's get started with solve the problem number 3. Let's consider this network consisting of 4 resistors labeled R1 through R4 as well as one independent voltage source Vs and one independent current source Is. The question now is to find the Norton's equivalent with respect to terminals A and B. Let's move on to the solution. By applying the Norton's theorem between terminals A and B, we can replace this circuit with a current source in parallel with the resistor, which will be denoted as IN and RN. I will start first with the determination of the Norton's resistance RN. This step can be done by removing all independent sources in the circuit, which means the voltage source Vs will be replaced by a short circuit and the current source Is will be replaced by an open circuit. The Norton's resistance represents the equivalent resistance between terminals A and B. That means Rn is equal to the series combination of R1 and R2 connected in parallel with R3, all connected in series with the R4. That means Rn can be calculated using the following formula: R1 plus R2 times R3 over R1 plus R2 plus R3 plus R4. And if we replace the resistors with their numerical values, we obtain Rn is equal to 20 ohms. After finishing the determination of the Norton's resistance, we proceed to calculate the Norton's current In. The Norton's current is basically the short circuit current calculated between terminals A and B. To find the short circuit current ISC, I will apply the mesh analysis method. It's evident that there are 3 meshes. This is mesh number 1, and this is mesh number 2, and this is mesh number 3. And I will consider IA is the current in mesh 1, IB is the current in mesh 2, and IC is the current in mesh 3. By applying Kirchhoff's voltage law in mesh 1, we can write negative Vs plus R1 times IA plus R2 times IA minus IC plus R3 times IA minus IB is equal to 0. And if we replace the resistors and the voltage with their numerical values and we continue simplifying this equation, we obtain negative 30 plus 25 times IA minus 5 times IB minus 10 times IC is equal to 0. Now by applying Kirchhoff's voltage law in mesh 2, we can write R3 times IB minus IA plus R4 times IB minus IC is equal to 0. And if we replace the resistors with their numerical values and we continue simplifying this equation, we obtain negative 5 times IA plus 21 times IB minus 16 times IC is equal to 0. In mesh 3, we can see that IC is equal to negative IS. That means IC is equal to negative 5 amps. Now by performing 1 plus 5 times 2, we obtain negative 30 plus 100 times IB minus 90 IC is equal to 0. Now by substituting 3 in A, we can derive one equation in terms of IB, And if we continue simplifying this equation, we obtain IB is equal to negative 420 over 100. We get negative 4.2 amps. And if we see here, the short circuit current ISC is equal to IB. That means ISC is equal to negative 4.2 amps. And we know that the Norton's current IN is the short circuit current calculated between terminals A and B. That means IN is equal to negative 4.2 amps. After completing the calculations, we conduct a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in SPICE simulator. This is the original circuit, and this is the Norton's equivalent circuit between terminals A and B. I connected a load resistor between terminals A and B to both the original circuit and the Norton's equivalent circuit, and then I will simulate their behaviors. And I also connect here voltmeter and ampermeter in order to measure the voltage across the resistor and the current through the load resistor. And here also I connect the voltmeter and ampermeter in order to measure the voltage across the load resistor and the current through the load resistor. Let's move on to analysis. DC analysis, calculate nodal voltages. We can see here that the voltage across the load resistor in the original circuit is equal to negative 7.64 volt, and the current through the load resistor is equal to negative 3.82 amps. And in the Norton's equivalent circuit, the voltage across the load resistor is negative 7.64 volt, and the current through the load resistor is equal to negative 3.82 amps. Through simulation, we can observe that the two circuits demonstrate identical behavior when we connect a load between terminals A and B. This outcome confirms the validation of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video, and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Norton's theorem. Take care and bye bye.